Yes. Okay. This morning I will be talking about AllegroGraph, and I will focus a little bit more on SPARQL than I normally do. My assumption for this talk is that the people in the audience already have read some stuff about RDF and RDFS. I'll also assume that people have read a little bit about SPARQL. Don't worry if you didn't read anything about SPARQL, because then this morning you'll get a little 101 on SPARQL just by looking at the examples. The general overview of my presentation is that I first will say roughly 10-15 minutes something about AllegroGraph as a product. AllegroGraph is a triple store, but it's actually a graph database with many different types of applications. One type of application that we'll talk about today is that it's a database for RDF and RDFS stuff, and the other thing is you can use it for social networking and social network analysis. If you guys are interested in that, I can talk a little bit more about that. To begin, my colleagues always force me to call this database a Web 3.0 database, especially the marketing colleagues. And why do they do that? Well, so this is a nice overview created by Nova Spivak, one of the players in this field of the semantic web, who did an analysis of technologies from, say, the last 30 years. And what you see here is that currently these are the things that are popular, and these are actually the things that we handle with our product. So in some sense we're really entitled to call this thing a Web 3.0 database. This aside, in the following I'll just quickly talk about RDF and triples, but again, as I said, I will assume that you know a lot about them. I will talk about AllegroGraph as a triple store, so how we work with RDF and triples. I will mention some advanced features that won't get much attention in this particular seminar, but at least I want you to know what we're doing. And then most of the time will be spent on giving you an actual demo of how you get triples in the database, how you get them out again, and how you work with SPARQL, and even SPARQL with named graphs. If there's time left, if people are interested, I could talk a little bit about the Prolog that we have on top of our triple store, and the range queries that we can do with a triple store. Okay, as I said before, I assume that you guys know what RDF is. It's a new standard. It's basically a standard for metadata in a meta language. The long-term goal is that every scrap of information on the web and in intranets has some additional metadata, and that will make life easier for agents and machines to help people search for information. Now, of course, this is a dream that is still a few years ahead of it, but the big surprise to everyone is that this stuff very quickly became a standard for metadata in general. And to some extent, this might all look new to some people, but people who have been doing a little bit in AI or semantic networks see that it's actually nothing more than a way to serialize old-fashioned semantic networks. So let me just do a little bit about RDF. Yeah? So let's start with a typical semantic network from the late 60s. This is everything above the line is an ontology, so you have things with a name, like there's a class mammal, which is a subclass of an animal which is of type class, and the mammal could have 2 eyes and 4 legs, and something like a dog is defined as a subclass of a mammal. And then in semantic networks, predicates are also objects with their own properties. So in this ontology, pet of has pet, owns. This one is an inverse of has pet. This one is a subproperty of this. Things might have a range, and things might have a particular domain. And then below the line, you have individuals that are described by the ontology. If we have some time in our presentation, I can talk a little bit more about the reasoning that we do. and why this ontology business is important. But the focus right now is on triple stores and SPARQL for today. Okay, so we had here a typical semantic network. Now, of course, a computer can't do anything with it, so it has to serialize this graph. And what it does, it serializes it into triples. So we see this network here. It's actually completely the same as what you see here on the left, except it's now done with symbols. And the terminology is that this thing is the subject, the predicate, and the object. In my presentation, I already mentioned the fact of named graphs, but please bear with me. Later on in the demo, I'll show you a lot more about the fact that recently triples became quads, and so now triples have an additional argument. Just for now, focus on the fact there's three elements to a triple. Now, one problem with this particular serialization of graphs is that if multiple people try to define an ontology, then very, very quickly you get into the messy business of name classes, and that people use different words for the same thing or give the same name to different things. So one of the really great things about RDF is that people made all these symbols unique by adding name spaces to them. So again, we see the same network as we saw in the picture. However, this time everything has a namespace. So for example, animal is now this particular namespace. You still have things without namespaces, then these things are called literals. But that's basically it. Yes, so triples and the elements of triples are made unique by adding a namespace to them. Now for some applications and for some people who really like XML, there's also an XML notation for triples. So let me go back. This particular way of writing up triples is called the ntriples format. Yes, so animal is of type class, mammal is a subclass of animal, etc. And then this is the XML way of representing triples, but I won't go into detail about this in any way today. Then triples might be in files, but if you then want to do reasoning on files or SPARQL on files, that will be cruciatingly slow. So what people do is they put triples in a database that is particularly designed for triples. We call these things triple stores. And how do they work? Well, most triple stores have this scheme, and we have that too, where you take a triple and then you replace every unique string with a number, and then you have a dictionary that provides you with a mapping from string to number, and a reverse dictionary that provides you from a number to a string. So again, these things will say animal type class, and one thing that you see here is the 6, meaning it's a triple number 6, so every triple has a unique ID. In addition, again, I told you we do named graphs, so this is a simplification, but I find that it's easy to explain triples when you first start with the triples, and then the named graphs is just an extension to that later. Now, triples are indexed. If you only look at the triples, they're indexed in 3 different ways. One way is to sort them, so you sort triples, or you put them in B trees, and you have a sort predicate, and the first sort predicate is SPO, subject predicate object. So say if you have an index for that, if you have that particular index, and say you do the basic call get triples, so find every triples where Jans something something, then in the B tree you will find where the first triple starts with Jans is in the subject position, and from there on you need one cursor run to find all the triples with Jans. Yeah? If you found all the triples with Jans Isse, then you would use the same index, and if you want to check that Jans is a psychologist, then you would use this particular index. If you don't know what the subject is, then you use this index, and if you only know what the object of the triple is, then you use this one. Now with the named graphs, there's actually 3 more indices that we use, and again, we'll do that later. Now, one question I get every time when I talk to people and do these web seminars is that people ask, okay, so can you help me understand what the difference is between a triple store, or the triple representation of knowledge, and the way relational databases store knowledge. And many times people say, okay, I have to tell my boss what is the difference and what are the advantages. So I use this simple example, and I'll use this example also in the demo that I give, where we have, here's some triples that describe a member of the Kennedy family. Yeah, so in this database we have a person of type person, with the first name Rose, last name middle initial is Elizabeth, and the last name is Fitzgerald. She didn't have a suffix, went to the Sacred Heart Convent for a school, was 105 years old when she died. She was a female. She had only one spouse, which is person 1. And then she had a bunch of kids, and one of her professions was homemaker. Yeah? Now this is a very flat representation of a person. The big difference with a relational database is that if you wanted to do the same thing, say, well, in whatever type of relational database, you would have a table for person with this information. Then because a person can have multiple spouses, you would have a link table to link people to people, to spouses. You might have gone to multiple schools, so you have a link table for that. You might have had multiple professions, you have a link table for that. You might have multiple children, so you need a link table for that. And then you of course have a table for schools, professions. And in the demo database that I'll show you later, we even have things like places with where people were born with longitudes and latitudes. But anyway, so this is what I call an artist impression of the same information in a relational database. And summarizing with a graph database, the one thing you can do is you can add many new predicates without changing any schema. So just imagine you're in an enterprise and you quickly want to add some new tables or columns to tables. In most enterprises you will have to go to the table committee just to get permission to add something new. Yeah. So now of course most enterprises would quickly run into big trouble if they really would change the relational database very quickly, but at least with a triple store you have the power to actually add many new predicates just on the fly. One-to-many relationships are directly encoded without the interaction of tables. So if you want to find all the children of a particular person in this database, it's just one call and you get all the children. And in a relational database, you really have to think all the time about the indices that you want to have, but while doing it you always realize there's a big cost of indexing your information in a relational database. With a triple store you don't even have that choice because everything gets indexed for you anyway, whether you want it or not. And that also allows you to do ad hoc queries much more easier than you would be able to do in a relational database. But I'll get back to that later when I show you some complicated queries. Now let me summarize what AllegroGraph is. AllegroGraph is a scalable, persistent triple store. So triples are stored on disk. Right now, we do 1.1 billion triples in 23 hours, which basically means that you can get 1 billion for $5,000. 2 years ago, I bought my first 16 gigabyte machine. Cost roughly $16,000, $70,000. 2 months ago, I bought a 16 gigabyte 4-processor machine with roughly a terabyte of data, and I could do it for $5,500. And that is currently enough to store 1 billion triples. And you can go to a website. Okay, well, on our website we provide some benchmarking information. Currently we load 20 to 40,000 triples per second, and we get record query performance on the Lubin benchmark queries. We're completely standards based, so we do RDF, RDFS, OWL, we do SPARQL, we do named graphs. If you use the triple store mainly for doing analytics, then what we see is people just build large triple stores by reading in RDF files or getting data from telecom databases or relational databases, and they put them all in a huge file, and they work as one person with this stuff, and then you work in a standalone version. And then we also have the mode where we have a client-server configuration where many people can all log into the same database at the same time. We are accessible from any language. We spend most of our development efforts on making sure that we are compatible with Sesame 2.0, and we also do the remote repository library of Jena. So Java people have the easiest way to connect to this triple store, but we also have a HTTP client interface where we have exposed the entire API of a triple store over HTTP, so you can use a REST protocol even from Ruby or Python if you wanted to. Then in our triple store we do reasoning. One way to do reasoning, if you want to do full description logic, is you hook up, say, to TopBraid Composer, and you can apply palette or other reasoners to it, or for large-scale work you can get Eraser, which is a full description logic, a very scalable one, to do your reasoning. And we have our own RDF reasoner. One advantage of description logic is that if you do reasoning, you get complete answers back, or a complete set of answers. A disadvantage is that our reasoners and full description logic work slow if the number of instances is very, very large. And we got many requests from the industry to provide something more efficient, so we disabled some features of OWL and enabled some other features, and now we have what we call RDF or an OWL Lite reasoner, which again will give you very quick answers but isn't entirely complete. Now we also have, this is the, well, you can't say traditional because this is all very, very new, but this is what you have in a traditional triple store. Then we have some very advanced features. One is, well, I talked about the RDFS reasoner. We do direct reification, meaning that you can have triples point directly to other triples. So if I have a triple, Steve is a man, and the unique ID of the triple would be, say, 111. Then I can have a second triple saying, Jans believes 111. Now this is very direct reification. You can very quickly say something about other triples. However, if you use this feature, then you live in sin if you want to be completely compatible with the RDF standard. But what we see is that most customers are really, really happy that they don't need 3 or 4 or 5 triples to say something about another triple. They take, well, they take the risk of living in sin and at least get less triples in the triple store. We completely support named graphs. So triples actually have a 4th argument. And this argument, and I'll show you that in the demo, but this usually what people do, especially people in the SPARQL and RDF community, they use that to cluster triples together. So say you have a file with triples that describe something, then every triple that comes from this file you could give the file name for the named graph. And that allows you later to say, okay, I want to reason but only within the file, the file name that I provided for the named graph. Or you can say, hey, delete every triple that comes from this particular file, and say you modify that file, you can read in the modified file again with another file name. What we also see is that people like to use this 4th slot for completely different things. In a telecom application that we built, we use the 4th slot. So I store, for example, the latitude in the 3rd slot in the object slot and the longitude in the graph slot. There's people that want to use it for provenance. There's people that do graph search in a triple store, and they use it to they use the 4th argument for the weight of the edge between 2 nodes. Anyway, you can use it for everything you want. Then another unique thing in our triple store is that, well, in most triple stores, everything is a string, and all strings are in a dictionary, which means that if you want to find every person between the ages of 10 and 20 in your triple store, you actually will have to go through all the triples where age is the predicate, read in using the pointer in the object slot to find the particular the age, you read in the age from the string, and then you do your comparison. With our system, we have a concept of immediate data structure. So in our triple notation, if things are numbers, then we can encode it directly into triples. They get completely sorted in our infrastructure. So for us, doing, say, finding someone between 20 and 40, or find a particular thing within a certain minimum longitude and maximum longitude, we can do that extremely fast. Right now, we provide basic geospatial and temporal primitives, and we're working on enhancing that set. We can do social network analysis, and if we have some time, we can talk more about it later. And we can combine all that stuff with Prolog and SPARQL. So far, the unique features of AllegroGraph. Just to give you an idea where we're going with this product, or what we can do right now. This is a simplified form of SPARQL. This is actually more Prolog based. So we can, with our system, already do queries like this, where we say, okay, find all the triples where Osama bin Laden controls a particular person X. I don't care in which named graph it is, and the ID of this triple would be this particular ID, and this might be already a RDFS inference. And then I use reification, so I say, well, where the CIA believes this particular triple, where the certainty is bigger than 0.8, so actually we do a range query here on the graph argument, where the graph argument is just a weight. And then we say where X was at a particular place at a particular time, so now you see that I use the time in the graph argument, where time 1 is after this particular date, and then I say find all the people that are 2 steps away from person X and put them in a group, and then find every person in that group, and then find for that particular person where he was at place 2 at time 2, and then find if these people were less than 12 kilometers away at the same time within 24 hours. Anyway, this is just to give you an idea of the power of this stuff, but let's continue and go on to the SPARQL. This will be ultimately supporting SPARQL, but let's now focus on SPARQL. Oh, sorry, got 3 more slides for the visually inclined. Basically, what this is trying to express, that we are completely standard based, and that we cover nearly everything in the W3C stack. This is the stack of our product, where we run on every platform. We have a compiler that will compile to every platform in machine code. On top is the graph database, which is nothing more than dictionaries, indices, and caches. On top of that, a simple API to store triples, to get triples back, and to read files. On top of that, an RDFS++ reasoner and Razor. And then on top of that, you can control all that with SPARQL and RDF Prolog. And if you don't want to use it in the standalone version, you can use it through our HTTP interface, or through our Java interface, or other interfaces. So let's go to SPARQL. 1 second. So as I said before, I'm kind of assuming that most of you have already read something about SPARQL. So I won't explain the syntax. I'll just give you a rough idea. In the demo, you'll get a 101, and after the demo, you should be okay in understanding what SPARQL actually can do. I always like to describe SPARQL as a mix between Prolog and SQL, where you run SPARQL queries against a triple store. There's many ways you can get information out of your SPARQL, and I'll give you an example, a few of those examples. There are some basic main controls. One of them is select, almost looks like the SQL select. There's an ask if you just want to know whether a particular query pattern is available in the triple store. There's a construct form where you can actually create new triples from the triple store. And finally, there's a describe query where you can get some more information about a particular resource. We can pre-compile our queries, so it's almost like stored procedures. And we have a And we have a lot of additional filter functions for the filters, but again, I'm now slightly jumping ahead of myself and using terms I haven't used yet. So let's just go into a typical query that you can do in SPARQL, and just imagine that you have a database with weapon systems and terrorists, and lots of information about terrorists. And actually, I can give you a little demo of that. I will give you a demo of this at the end of a demo. And I think that most people in the audience will be able to read this just to help you. So here you say, okay, find every A, B, X, and P where Osama bin Laden influences a particular person Z, where this particular person Z has a friend B, where this person has been in region D and B has been in D, and then a completely new person A is acquainted with B, where A was an airline pilot and B was an airline pilot, and B was born in a place where a new person was born, was also born, and this person has a belief system P. Just imagine you write that in SQL. I usually find by just showing this that you already can show the power of SPARQL as a graph matching language on top of triple stores. Now let me go to the demo. Okay, no, let's stop. Are there any questions so far?
Okay, 1 second, Jans. A lot of people have signed in before I announced that I've muted the audience. So if you have any questions, press 6 to unmute your own phone.
So again, if you have a question, press 6. Okay, no questions. Let's go into the demo. Now, some of in the audience will use something like AllegroGraph from Java. Just a few notes. I mean, I just want to make sure that you understand we can do this from Java. This is the Sesame interface, or mostly part of the Sesame interface. Here we define a new connection to a triple store. We give it a particular name, we give it a particular directory, and then this call will start a new triple store and delete the old one if it's already there. That's what the renew does. We can add triples from the triple store very simply by doing the add statement. So find every statement, add statement with sub predicate object 1 and sub 1 predicate to object 2. Then, if you want to add stuff about the same subject, we have some syntax to make that easier and type less. If you want to get triples out, we use a function called get statements. Here we define wildcard to be the null string. So basically what this does is you create a cursor CC that gets the statements, that finds all the triples, and where you don't specify the subject, predicate, and object. So basically it means you get them all back, and then you just step through your cursor and you have all the triples in Java memory. So this is the only Java I will show today, but just to make sure that you understand that we provide a full Java API. Java API you can find on our website if you go to our documentation. From now on, I will do all my demos in Lisp because I want to give you some interactive demos very quickly, and Lisp is slightly better suited for interactive demos. So here, I dive into Emacs. On top here is a file with scripts, and people that are interested can get this particular script. And at the bottom is what we call the listener, so I can type in stuff like and I can define a function. Yes, this is basic Lisp, but just look at this as a scripting language. The whole triple store underneath is written in Lisp, and so right now I'm working in standalone mode. So let's just load in the triple store. Now, like Java, we have the concept of package names. So while working in interactive mode, I want to use only symbols from the package TripleStore user. Actually, what happens is I'm here with my cursor in the script. I press a button, it copies this part to the lower part, and it executes it. And now you see that the package is changed to TripleStore user here. Let's create a TripleStore. So we have we created TripleStore seminar DB. We put it in the directory temp. If it already exists, we supersede it. So now we have a empty TripleStore. Now, because all of us are lazy, we don't want to type namespaces ever. Yeah. So what we do is we create a namespace, in this case called O, which is the same as this expression. And basically what it does, let me execute it. So if I now would type bang O person 1, I get the full expansion of person 1. Yeah, okay, so if we understand that, I can add some triples. So let's say person 1 is the first name Steve, he's an organizer, and he's 52. So now we have 3 triples in the TripleStore. Now let's add some triples about myself. Person 2 is the first name Jans. He's a psychologist. He's 48. Yeah. So now I have 6 triples in the TripleStore, and now I want to print all the triples that we have. So one way to do it is do list for every triple in get triples list. Get triples list is a form that if you don't give it any arguments, it will return every triple in the TripleStore. So usually you don't want to do this. Yeah, but this is only 6, so we can do it. And then we print a triple. So do list for every element in this list, print a triple. I do that and I get these triples. I could even write these triples to file and read them in again. Yet it's the n triple notation. Now, because I don't want to type this whole stuff every time, I wrote a little function called show triples, which basically does this. And it only uses the short names. So this looks slightly better and more readable. Now let's start working with getting triples out of there by using the triple patterns. So this one says, show me all the triples where the object is a psychologist. So this one will go in the OSP index. Yeah, and so we'll find person 2 is a psychologist. I'll find every triple where the predicate is first name and the object is Steve. Yeah, and I get this triple back. Now I can get a triple if I do get, if I say get triples list, I get things back. Actually what you see here is triples in, actually what you see here is a list of C structs. Yeah, this full of hash codes and all kinds of unreadable stuff, but basically think of it as a C struct with a subject field, predicate field, object field, graph field, and a unique ID field. So let's set the triple to the first element of the last expression. So now we have one triple, and just to make sure type of this triple. This is going a little bit technical, but actually it's a simple array of unsigned by 8 and it's 56 bytes long. Now usually you never will work with that, but just, so what we do, we also have a call called symbolic subject, and here we see that the first triple is just person 1. Okay, let's now delete triples. So that I'll delete all the triples where the subject is person 2. So let's delete me from this little TripleStore. If I now print all the triples again, I only see the triples about Steve. And then I close the TripleStore again. So what we've seen so far is how do you open the TripleStore, how do I add triples to the TripleStore, how do I delete triples from the TripleStore, how do I get them out using a triple pattern, and how do I close it again. This is the very, very basics. Now for our SPARQL example, I want to do something slightly more interesting. So we have a database about the Kennedy family. And let me show you the Kennedy family and triple file. So here, this is a file with, I think, roughly 1200 tuples. So here we see person 1, first name Joseph, middle initial Patrick, last name Kennedy, suffix none, went to Harvard, was less old when he died than his wife, he was a male, and then lots of children. And then later on in the demo, you even will find things as places where people were born and their longitudinal latitudes. Yeah, so this is the basic the basic representation of the Kennedy family. It's a whole genealogy. Now let's fill the database. So we say create a tuple store seminar again, and if it exists, supersede, then load the n tuples from the Kennedy file and index all the tuples. So we'll do that. We'll first tell lister we want to have this function. Then we read the 1200 tuples, in this case roughly 50 milliseconds. And just to make sure that the tuples are in there, I do this call show triples again. I say give me all the tuples where the object is male. And here you get the whole list of all the males in the tuple store. Okay, so now let's go to SPARQL. Before I continue, just to make sure that I don't lose anyone, any questions? Again, press the 6 if you have a question.
Assuming that you can do all these in Java API as well, right?
Everything what you saw so far is completely supported in the Java API, yes.
Okay.
So let's do some SPARQL. This is the syntax of SPARQL, but because we run this in Lisp, I say run SPARQL, and then an argument is a SPARQL query. Yeah. Now the first construct that we talk about is ask. If you want to know whether a particular pattern exists in the tuple store, then you don't have to create a whole list of things that you get back. What you just can do is do an ask query. So basically what you look at this. First you define what you do in SPARQL is you define a prefix. This prefix is O in this case, and it says whenever you see O colon, replace that with this particular URI. So, and then I say ask, meaning don't give me any results back, just tell me if the following pattern exists. And then you say, is there an X that has the sex male? And then the semicolon means the next clause is also about X. So actually, technically, it would be probably slightly more readable if you put X there again. But this syntax is say, and this particular X also went to his alma mater, Harvard. Okay, so this is one of the simplest queries you can do on the Kennedy database. So you do this, and you get a result back, basically saying yes, it's true. This is the list notation of true in other languages. So you should read this as true. Yeah, we just say T. Now, asking is just one thing, but most of the time you want to know who these X's are. So what you then say is select. So basically you see the same query. Let's do first we have to do it without counting. So now you say, okay, give me all the X's back where X is a sex male and this X went to Harvard. So you do this, and what you see below is that person 4 and person 1 and person 17 and person 3 and person 47 went to Harvard. So there's 5 people that went to Harvard. Now what select also lets you do is you count how many times things happened. So you can add to our queries that you want to count. This is something outside of the SPARQL spec, but in many cases, if you work with SPARQL, very, very handy to have. And we have opened up this API to Java too. So in Java, you can specify for a SPARQL query how many solutions there are. It's a little bit like count in SQL. So let's do the same query again. And what we see, what we saw before, there's 5 answers to this query. Now, personally, I always use SPARQL JSON because for me that's slightly more readable than XML. At least takes less space, so I can do the same query that I did again here, but now I use the results format, SPARQL JSON, and we support a long list of external formats. Just look in our documentation for all the things we support. And so let's go to the other side. So again, the same 5 people now with in JSON. JSON, by the way, I don't know if you all know it, is something that was made by JavaScript people to make it easier to handle XML. Now, if you run this stuff in Lisp and you're doing all kinds of complicated reasoning, then in some cases you don't want to work with the strings that you get back, you just want to work with the internal representation of the database. Yeah, so you don't even look up in the dictionary what the internal numbers mean, but you just do all your hash operations and what do you have on the straight representation. So we can do this internally, and now I get all the X is just the parts back in the internal format. This is just the same one, but now we ask for 2 queries. We now say select XP, and in itself that's not a very interesting query, but let's do it anyway. So what we see now is all the professions of people. So every profession of every male person in the database. And now let's filter it. Yeah, so one thing you do with SPARQL is you first specify a pattern of things you want to get back from the tuple store, and then you have a way to refine your result set by applying a filter to it. And so, say you wanted to find all the attorneys from this particular database, you would have the same query that we just did here, and then you say, and then filter using a regular expression all the P's, and only give me the ones that have the word ATT in it. So I run SPARQL, and now we go to the result set, and what we see is only one person, which is person 47, who was an attorney. Another construct in SPARQL, which is quite unique, is called the optional. So we see the same query that we saw again. Find every X that has the sex male, where the alma mater is Harvard and where the profession is P. But then you say, if this person also has a child that went to the same, or that also has an alma mater, then return that too. So if you don't have children, then you still get a result back. But if you get children back, if someone has a child, you get those results too. So let's look at that output. So now what we see is that, for example, let's see, this person here was a congressman, but didn't have children, so the only thing we get back is the P and the X. Whereas person number 20, person number 4 was a congressman, but also did have a child Y, so he gets this thing back. And I don't know if there's someone who then again went to the school. Again, if you have any questions about that, just press the 6 and ask me questions. Yeah, so this is the optional part. Then we have order by. Again, everyone who knows SQL knows about this construct. So what we've done now, we took the same query again, but now we ordered by the profession. So if we look at this, we should see that the first person we see here in the set was the attorney. Someone in the army, ambassador, ambassador of course comes before attorney. Yeah, so now you have ordered on a particular result in the result set. Now, some of our customers already run this SPARQL on larger or really large sets, and one of the things we always warn them about is that order P, yeah, it will work, but if you don't use order, the results are streamed back to you. So we don't build up a complete result set of SPARQL queries in memory. If you normally do a select, all the results are created on the fly and sent back to the output. If you do an order by, there's nothing we can do but get all the results in memory and then sort them according to something. So it's something really you have to watch for if you want to use order, because order just means sorting and keeping stuff in memory. So if you can afford order, please do it, because it's a lot cheaper on resources. Then there's a thing called limit. So here you say, okay, order by P again, but limit 2, but show me only the first 2. So here we'll see that we get the ambassador and the army. We get the first ones back. Now mostly you want to use limit to just get a quick answer back. If you use a limit in combination with an order, you of course first have to order everything sorted, then you give the first 2 back. For small databases, great. If you have millions of results, you have to pay the price of doing this over millions of results. Then we have this thing called construct, where
can you do paging? Like you can say starting from the second page.
Yes, we have that.
Okay.
We have it's not paging. It's how do you call it?
Scrollable or something. I mean something like you can select. You receive a portion of the results and still scrolling through it.
We support a syntax where you say start at the 5th element of the result set.
Okay.
So you can do order by and then I forgot the name. Start at, begin at. I forgot the name. It's in our documentation, but you can start at a certain place. We have this thing called construct, where you can use SPARQL to actually construct new n-triples. However, you have to be aware of the fact that these triples are only in memory, so you as the programmer or user are responsible for saying store these triples. But let's just see what happens. So you run, say you create new triples where you say X is the grandfather of Y. This is like a very limited, simple way of reasoning. Where X is male, where X has a child C, and where Z has a child Y. Yeah? And then you say return stuff back as n-triples. So now if I run this part, I actually created all the grandfather of pairs in the triple store, and if I wanted to, I could store these things in the triple store again. Now, we're also working on update, where you actually can specify in Spark, but the SPARQL standards group is working on specification of update, so that within a SPARQL query you actually also can save the triple straight away. But we're waiting for that particular standard to close, or at least to get to a draft that we can implement. Then named graphs. I told you several times about that, so let's use it. Let's create a new triple store. So we say create a triple store again, put stuff in seminar, if exists supersede, so we override the old one. And now here we say load n triples, where the default graph is Kennedy file. And then, so basically say for every triple in the file candidate n triples, add as the fourth element the named graph Kennedy file. So we execute that, we fill the database, and now we have a bunch of triples all with the fourth argument Kennedy file. But now let's add some triples with another different graph. So one person in the data, well, let's add a person 1000 with the first name Arnold, and the named graph for this triple is interactive. It could be any name, I just chose interactive. And person 1000 is the last name Smith, also interactive. And then person 1000 has the profession professor in the interactive graph. So the first thing is I say, show me all the triples where the object is Arnold. And what I see is that there's a person 27 with the first name Arnold, and I can already tell you that his last name will be Schwarzenegger. And then there's this other Arnold, which is Smith. Yeah. So let's find all. Now let's do this thing. Show all the triples where the graph is interactive, and we'll find Arnold, last name Smith, profession professor. So now we run SPARQL. First, we run SPARQL without mentioning any graph. So we just say, hey, find every person with the first name Arnold and the last name is last name and he's profession professor, and give me the results back in JSON. So I do that. Then I find there's a guy Schwarzenegger that's an actor, a Schwarzenegger that's a governor, and Schwarzenegger that's a bodybuilder. And then there's a guy Smith that is a professor. Yeah. Now we want to select only the Arnold from the Kennedy file. So now we have this extra clause here where we say, okay, do the same SPARQL query, but only give me the people from the Kennedy file. I'll only look in the Kennedy file. So I do this, and I go down, and now we only have the actor, the governor, and the bodybuilder. And if I would do the interactive one, let me see, where's the interactive one? Okay, let's do the interactive one first. I run SPARQL, and I only get this Smith back, who's a professor. So now, just for fun, let's delete all the triples. So now let's delete all the triples from the interactive graph. So I do this. Let's go here. I delete the triples. And now I run the same query again. And now we see there are no results. Okay, that concludes my demo for now. And I want to give you guys a chance to, and girls, to ask some questions. Please press the 6 if you have a question.
Jans, I think you've done a very concise job today.
1 hour.
So,
it's a record.
If there's no questions, I will be sending out a questionnaire survey. We like to get feedback on these. We keep evolving this and adding new components as we determine the interest of our audiences. And I have an 85% hit rate at recording these sessions, so if everything went well, I'll be able to post this. I'll send that in the email as well. So if your colleagues would care to visit this, or if you'd like to revisit it, you'll have the opportunity. So one last chance for questions. Otherwise, yes?
Yeah, I have a question.
Okay.
I was wondering what kind of backup facilities or transaction support you have on your database backend.
The backup, yeah, we have a backup strategy. Basically, the triple store consists of many different files. There's two files that are crucially important, and we have a procedure to back those up. And with respect to the transactions, if you use the HTTP mode, we do provide transactions, because then all triples will go in, or none of the triples will go in. On the Java side, the Java programmer is responsible for making sure that the bunch of triples that he wants to add to the triple store are actually correct, because once you give them to the AllegroGraph, they really go in. There's no rollback right now on the triple store.
Okay, but at least they'll know whether it all went in or all didn't go in.
Yeah, they all went in or they didn't go in, yeah.
Okay, and the backup will only back up what's been committed or not?
We have a transaction log. So every time when you add a triple, it goes to the end of a transaction log. And you can keep, so you can, very simply, you can even use rsync to do very quick backups of a particular triple file in the string file. And you don't have to do the entire one. I mean, rsync will only give you the blocks that were changed since the last time you used this.
Okay.
We can help you with that.
All right, thank you.
Is there a reason that you didn't show the any reasoning capability in this demo?
Yeah, we wanted to do this thing in 1 hour.
Okay.
Because, and then, so we could organize another meeting for this thing about reasoning, for example. Basically, we're doing these seminars also so that we get a recording of what I do, so that everyone then can actually just go to our website and just look at this stuff at their own leisure. So one of the plans we have is to do the same thing for reasoning, one to do for Prolog, one for the HTTP interface, maybe one just for Java interaction.
Okay.
Yeah.
Okay, are there any more questions?
Yeah, I have a question. Is the SPARQL interface that you're using from Lisp, is it targeted only towards AllegroGraph, or could you target it towards some
it is
XML-based stuff in genome?
It is a so we do the SPARQL HTTP interface. So SPARQL has its own HTTP protocol. Yeah, so we can use our SPARQL to talk to a Jena database, or sorry, to a say a Sesame database, because they do the SPARQL HTTP protocol, we do the SPARQL HTTP protocol.
Got it. Thanks.
But in addition, you can use, well, our HTTP interface also supports SPARQL. For Java, you can send SPARQL, but then of course it goes to our triple store. But you can use the originals, the thing that is in the SPARQL spec, and it will run against other databases. But then you don't get all the additional features that we have. Yeah.
Any more questions? Okay, I want to thank everybody for attending. Good session. We got it all in an hour. Again, I'll be sending out a survey questionnaire and have a link to a recording of this session. Once again, thank you for attending.
Thank you.